through this recipe for how we designed, well, I didn't design, but how HACC was designed in some sense, hopefully in a way which will enable you to apply these various concepts to other problems. And I will also go over some various lessons that we learned in the process of optimizing the code, specifically on the Blue Gene, and then Nick is going to talk later about things that we do on the GPU systems. So most of these things here are things that I've learned either from Salman or from Vitaly, who's one of the performance engineers at the lab. And so I didn't think about almost any of these things by myself, but hopefully I'll be able to distill them in some way, which is. So this is the first recipe. The first recipe is separation of scale. And the core problem, as Salman described it, was that we have this huge n-body problem to solve. It has trillions of particles. So obviously you can't do an direct n-squared computation, because that would be a trillion squared. And even with modern supercomputers, you just don't have that kind of flops. I mean, that's just for one time step, or one force evaluation. You may have multiple of those per time step. I mean, nevertheless, it's just not doable that way. Luckily, people over the last, 100 years or something have been pretty smart, and they've come up with more efficient ways of doing this. The most efficient way that we know about is actually to use a Fourier transform, a grid technique, where you have a grid and you deposit the particle density onto this grid, and you use a set of discrete Fourier transforms, right, which are efficiently computed using the fast Fourier transform algorithm, which is an n log n algorithm. And if you do that, that is really the most efficient way that you can compute these n-squared interactions, especially considering that we have periodic boundary conditions. That's great, so we should just do that, except that we can't. And the reason that we can't is because we have a huge dynamic range, as someone showed in that picture. The simulation is sort of dense with structure more or less everywhere. If you really tried to make a grid that had a uniform grid spacing that was fine enough to capture all the detail that you needed, you'd end up with something on the order of like 1,000,000 cubed. And you just don't have that kind of memory. Here's the problem that we have. We have a really efficient algorithm to do this problem. But to do it on all scales requires much more memory than we have available. So what do? And so here's the answer, or at least our answer. So our answer is that we separate the scales. We want to use the really efficient algorithm for as much as we can, and then we do something else for those finer scales that we can't capture with the really efficient algorithm. We take this function, this Newtonian force law, more or less, and I say, OK, this is a function. Well, I can always write a function as the sum of two other functions. And this is exactly what we're going to do. I'm going to take the force. I'm going to say, OK, I'm going to divide it into something that I call the long-range force, which I solve with this grid and the FFT, all the other machinery that implies. And then I'm going to have whatever is left over, and I'm going to call that the short-range force. And the force between two particles is a function of their distance, and so this is a function of the distance. And I'm going to say, so I have this long-range force. And this I'm going to solve with the FFT. This actually gives us a number of advantages, not just the fact that we can solve this with the FFT. Another thing is that, well, this is a sort of classical physics problem. And the nice thing about this classical physics problem is that when I say I'm restricting something to long spatial scales, I'm also restricting the characteristic time scale of those interactions. So things that handle forces from things that are far away, those forces probably don't change very much compared to the forces from things that are close by. Just because if they were changing really quickly, that would mean the far away stuff was moving a lot relative to you, be going super fast, which it's not. Not only do you get this separation of scales where you get to pick the sort of algorithm that you really want to use for most of the problem, but you also get this advantage that you don't have to do it as often. And you get to subcycle. You get to do the short-range computations on more often compared to when you do the long-range computations, because that's where you need the time resolution. You don't need it for the long-range interaction. In addition, because of the way this is done, the short-range interactions are now local to every node, to every rank. And so we really get a number of nice advantages out of just saying, well, I'm going to take this function. I'm going to write it as the sum of two functions, one of which is the algorithm I'd really like to use, And the other is, well, whatever I need to do to take care of what's left over. So then, of course, we have the next problem, which is, so I've determined what I want this long-range force to be. The long-range force is whatever the FFT-based Poisson solver gives me. I'm going to deposit these particles onto a grid. The grid is going to have some finite scale. And so it's going to smooth the density on that grid scale. You just don't see anything smaller than the grid scale when you put the particles on the grid. And that's going to give you some effective, softened grid force. And on long length scales, it's almost exactly the answer that I want. In fact, it is, to within the error of the solver, exactly what you want, so you're done. On short length scales, it's not what you want, because you've now smoothed out the density, you've smoothed out the force. You're not resolving the force on scales that are smaller than the grid scale. So I know what this is, at least effectively. If you're clever about it, you can do things like write down analytic formula to describe what the softening is and other things. But as it turns out, you actually don't necessarily need to be all that clever about it. You only have to know some basic properties of the thing that you're solving. So in this case, we know that this force is roughly just a function of the distance. And, excuse me. And so we can just determine what this effective force is empirically. We could take a bunch of particles, place them on a grid, different distances. We could run the long-range force solver and map out what the effective force is that this thing is computing. And we know analytically what the force that we want to compute is, right? It's like this Newtonian force law. And so I can take what I want, I can take what I have, I can subtract them, and the short-range force is the thing that's left over. That's the thing you need the short-range force solver to compute for you to get the answer that you want. And then the question becomes, well, okay, fine. Well, how do you compute that? The answer, since this is portable performance, I'll tell you that's the non-portable part in some vague sense. That's the thing that's going to depend on the architecture. Different architectures will have different optimal ways of computing this short-range interaction. And I'm going to tell you about how we do this on the Blue Gene, and this is going to tell you about how we do this on GPUs. And there are a lot of similarities, but there are also some differences. So this graphic was in Salman's talk as well. And it's just to give you another visualization of exactly what I'm talking about. So you start off with all these particles, and you deposit these particles onto a grid. When the particles are far away, this is almost the exact answer, because this particle, say, is only in this grid cell, this particle is mostly only in this grid cell, and there's not much else to do. The problem comes when you have particles that are closer to each other than the grid cell spacing, because the force solver is going to smooth out that force. It's not going to give these particles a lot of force in between each other. And obviously, since it's gravity and these things are supposed to attract together, if they don't attract together, then you get the wrong answer, right? So, okay, not to belabor the point, but this shows you how we split up the problem. So the long-range force solver handles the sort of long-range interactions, and then we have architecture-dependent methods for doing the short-range. On a CPU system, we use something called an RCB tree, so a recursive coordinate bisection tree. If you know about multipole methods, you can kind of think of this like a first or second order multipole method. And then inside that, we use some little n-squared problems, which is this pp in this square here, where we actually directly compute the forces. I'll say more about that in a minute. The way this turns out is that they say the largest, like 4 orders of magnitude, are handled by the long-range solver. And the inner 2 orders of magnitude or so are handled by the short-range solver. And so the long-range solver is this nice n log n algorithm, where this scales as the number of grid cells, or the number of, the net number of cells in the grid. Then we have tree algorithms, which are also n log n, but those scale with the number of particles. And then we have short-range interactions, which are n squared. And you might say, well, why would you use n squared for the really short-range things when you already have a local n log n solver? And it turns out because asymptotics aren't everything, right? All asymptotics have a coefficient in front, and the coefficient can be large, and here the coefficient can be small. And so for some value of n, it's cheaper to do n squared than it is to do n log n, because there's overhead to the n log n algorithm, which is something that's always really important to keep in mind. And just to give a little bit more detail about the long-range solver, just to give you some idea of what's going on, is that in order to in order to compute this force, there are a bunch of different things that have to go in this. And I bring this up only to say that sometimes the most naive thing to do is not always the best thing to do. For instance, when you do the deposition of the particles onto a grid, there's a discretization error that you get, and some of that you can actually correct for in the Fourier space kernel that you're using to compute the force. You can wrap it all together and do one sort of combined solve that also corrects for some of these errors. And you should talk to us about this afterwards if you're interested, but I just bring this up because it's an example of one of the kinds of things you want to think about, especially if you have a spectral method. So another thing that I want to bring up, this is my recipe, is if you have a spectral method, remember that spectral methods are really, really good at computing derivatives. I've actually seen codes that compute things in Fourier space, invert the transform to bring those things back into real space, and then use a stencil to compute derivatives. This is actually really, really dumb. The stencil will have a local, error that's like, order of like the grid spacing squared, or if you're really fancy, use a fourth order stencil or something, the grid spacing to the fourth. The error when you compute the derivatives in Fourier space is exponentially suppressed, and it's a local operation in Fourier space. It is if you have a spectral method and you need to compute derivatives, please do it in Fourier space. You do not want to do anything else. So in any case, most of this I've said before. The other thing I want to point out, which is actually quite important, is this point about how we use mixed precision in HACC. I know a lot of people have talked about mixed precision codes. Actually, on the blue gene, it doesn't really help you all that much because the single precision and double precision instructions executed at about the same rate. But even there, it helps you with memory bandwidth. So what we do is we use double precision to do the long-range force solver, because there we have a much larger range of distances and values, and it's much more difficult, especially with the FFT, to keep precision, the necessary precision, if you're only using single precision numbers. But for the short-range force, where everything is fairly close together, the dynamic range of distances is not that large, dynamic range of velocities also isn't that large, we can use single precision. As I said, on the blue gene, it hasn't actually helped us all that much because the instructions themselves in single precision don't execute any faster. You don't get to pack any more of them in the vectors or anything else. But even there, if you're bringing in a bunch of single precision numbers, they're still only half the size each of the double precision numbers. So you're only using half the memory bandwidth to bring in single precision numbers as you are to bring in double precision numbers. So even on the blue gene, which is not really the poster child for mixed precision computing, it can help quite a bit. If you go to a machine like Titan, and I'm sure Nick will say something about this, the K20Xs on Titan will execute single precision instructions. The peak is quoted at 3 times the double precision rate. It really does behoove you to think about where you can use single precision, even if you cannot use it everywhere in your application. It really can give a nice performance boost almost for free, in quotes, and it is something that you really should think about when designing a code, where you really can use lower precision numbers. I was at a talk last week where speaker was talking about some sort of lattice QCD code, I think, and how they accelerated it on GPUs. And there they were saying that for some of their problems, they even go down to half precision because they get a nice speed up from that. You can also, not we do this in HACC, but if you have an iterative solver, you can often do the first set of iterations in lower precision and then only boost up to higher precision when you actually get close to converging on the answer. So Salman also mentioned this overloading. Now this is another design consideration that was put into the design of HACC. So most codes, when you divide them up spatially, you end up with some kind of ghost region. Right? The ghost region is just the area on rank A that kind of replicates data from its neighbor B, C, D, whatever. The idea is that when you're doing some sort of local computation, when you're near the edge of your assigned volume, you need to know what's on the other side because those things are local to your region and they need to go into the calculation somehow. And there are lots of different ways of doing this for different kinds of algorithms. It turns out that we have a really big advantage when simulating the universe. And the advantage that we have is compared to the size of the universe and the timescales over which we're simulating, the bulk motions of large structures are small, and the structures themselves are compact in size. relative to how much volume is on each rank. And so it's actually feasible to make your ghost regions large enough that they essentially will always contain any large structure, any significant structure that happens to be on your neighbor near you. This gives a really nice advantage in the fact that we do not need to refresh those ghost regions, in other words, populate them from the neighboring ranks every time step. We don't even have to do it every time we do, we don't have to do it every time we do certainly don't have to do it every time we do a short-range force evaluation. We don't even have to do it every time we do a long-range force evaluation. It can be several time steps to go by before we have to refresh these ghost regions. This is something that is really physics-driven. I don't think that you can apply this to a large range of applications, but it is something to think about if you have set structures and you have relatively slow, bulk motions of information transport in your simulation, is that you may be able to cut down on the amount of neighbor-to-neighbor communication you do by doing more compute locally and by taking a hit on your memory overhead. And in fact, this helps us quite a bit because these particle exchanges would still exchange a fair amount of data. And if you look at a node, right, the largest volume per slice, right, is around the outside. So you have to, if you cut down the exchanges of those ghost regions, you've cut out a lot of the communication that you'd have to otherwise do in a code like this. Cutting out communication is, I think, generally a good thing because, as Jeff so nicely demonstrated, the performance of various communication primitives on different machines is highly variable and often doesn't quite scale the way you would naively expect. Getting rid of that makes your code more predictable, if not more performant. So the typical memory overhead that we use for these ghost regions is about 10%. So I said it takes a memory hit, but it's actually not a huge memory hit for a large run. That having been said, I say for a large run of 10%, it also, the amount of memory overhead that goes into the, these ghost regions, these overload regions, goes into the calculation that we make of how we set up the runs. So, you have to be careful about that. But we can find configurations where it's not a particularly large fraction of the overall volume. I'm just going to make a quick comment about the time stepping, just because we haven't said anything about it yet. And I'm going to say that we use a split operator method. There are lots of split operator methods that are around for various kinds of problems. They're certainly worth looking at if you don't know what they are. And it provides a very natural way of what I called before subcycling. In other words, doing short-range computations more often than you do long-range computations. So what we do is we take the overall time step and we divide it into several pieces. This is a generic operator splitting method. And so what we can do is we have these long-range pieces, sort of long-range half pieces, which if you replicate this over here, you could combine this one with the next one in most cases. And then the short-range piece, which can get replicated some number of times. If we're not doing a hierarchical time stepping, this number of times that we use is generally something between 3 and 5. It's less if you're doing hierarchical time stepping, but I'm not going to talk about that. But I am going to talk about how we do the short-range computation, how this n log n tree algorithm works. I'm not going to explain a lot of the details, but I do want to point out a couple of key features that are germane to this portable performance concept. I don't know if any of you have heard of this concept of cache-aware algorithms or cache-neutral algorithms, cache-conscious algorithms, whatever they're calling them nowadays. This is one such algorithm. The idea is that you design the algorithm in such a way that it recognizes that CPUs have caches and that you want to keep data as local as possible to data that will be accessed with that data. And you do this without really programming in details of the cache structure on any particular machine. So in other words, this data structure was designed with keeping in mind that CPUs have caches, but there's no parameter in the data structure that says what's your cache line size. That kind of tuning actually turns out in most cases to be unnecessary, which is quite nice. The way the data structure works is the following. So you have all of your particles. Remember, now we're only talking about the short-range force because we only use the solver for the short-range force. So here are all your particles, and you need to compute the force on every one of these particles by every other one of these particles in this region. And so what you do is you start this recursive decomposition. So first we pick some dimension and we divide it such that you have roughly the same number of particles on one side of the division as you have on the other side of the division. It's the so-called center of mass division. Then you end up with two regions and you do the same thing again. And then you do the same thing again, you do the same thing again, until you end up with a number of distinct regions. We call these leaf nodes, because if you're in a tree, these would be like the ones at the end, so the leaves. And each one of these nodes, this is the important part, has two properties. One is that they all have roughly the same number of particles. This is the key thing about doing this division such that the number of particles on one side is about the same as the other, is that at the end, all of these things have about the same number of particles. And when a few slides when I say something about concurrency, this is extremely important because it balances the concurrency. The other thing is that every time we do one of these splits, we actually partition all the particle data. So we take the set of arrays that held all the x positions and y positions, et cetera, of all of these particles. And when I split this in two, I actually take the array, and I say, OK, I'm going to partition these things. It's like a partial sort of all the particles. And I take all the particles that end up on this side and put them at the beginning of the array, and all the particles on this side and put them at the end of the array. And it does this recursively. So as a result, not only do all of these partitions have approximately the same number of particles in them, but all of that particle data is contiguous in memory, is what gives the nice cache locality benefit, because when you have the short-range solver going through and accessing this particle data, when it's looking at this particle, probably the next thing it's going to do is look at that particle. But since all of those particles are near each other in memory, then once it brings the first particle into cache, it probably just brings the second particle into cache. And so that obviously is much more bandwidth efficient than if you just were, say, storing pointers to these particles or indexes and reordering those. So even though the partitioning is more expensive than just, say, reshuffling an index array, because the expensive part of the computation is not this. The expensive part of the computation is actually doing the force computation. You save much more doing the force computation than you would ever lose by resorting the data. When you're computing the forces using the tree structure, there are two parts to this. So one is that you go through all of these leaf nodes with all the particles. And you say, OK, so for each of these leaf nodes, I'm going to interact you with all the other close knit leaf nodes. For these pairs of interacting leaf nodes, you do a little n-squared computation. Two parts to this, as I said. One part is building up a list of particles with which you're interacting. And the second part is actually computing the force of all the particles in your target leaf node with the particles in your interaction list. Now, building this list involves walking the tree. You have to walk up and down the tree structure to collect the particles. That way you know which particles are near you, and then you actually do the computation. Now, this walking procedure is the n log n part of the algorithm. And you can say, well, if you actually had each leaf node only have one particle, then the whole thing would just be n log n. You'd be done in some sense. The problem is that the tree has to be pretty deep to do that. I mean, you build the tree all the way down to single particles. And yeah, it's n log n, but there's a pretty high coefficient on that n log n, because you're doing pointer chasing for every particle. And turns out that's a really bad idea. The other thing is that, compared to the memory bandwidth, you get a certain number of sort of flops on the CPU for free, right? There's a certain amount of computation that you want to do to amortize your access cost. And anything below that, it doesn't really matter. I mean, you can do free compute in some vague sense. And so the other thing is that since we have more than one particle in every leaf node, you have fewer nodes in the tree. And so the walking itself is cheaper. So this is the trade-off that we make. We do these local n-squared computations, where I do a whole leaf node versus a whole other leaf node. So you're doing more, in some sense, more computation than you need. But it makes the tree shallower, which makes the walk cheaper. And if you look at the trade-off, the wall time optimal configuration, in other words, the time that gives you your fastest time to solution, is actually to use some number of particles in every leaf node. Not thousands, but modern x86 machines, we find the number is like 20. For the blue gene, the number is like 100. But nevertheless, the wall time optimal configuration actually involves some amount of n-squared computation with some amount of tree walking. And exactly where that line is different depending on the machine. One point I want to make about this is that in terms of portable performance, is that I think just about every algorithm I know that really gets really good performance on modern machines has some kind of set of tuning parameters in it. And you often can't set these parameters from first principles exactly. So, I mean, the blue jeans actually have a pretty simple CPU on them. And you can do a back-of-the-envelope calculation and convince yourself that the number should be somewhere around 100. But exactly where it is, it's hard to say. On an x86, I don't even know how to do the calculation. So you just have to try it and find what the number is. But nevertheless, you get these tuning parameters. I think that it's a mistake to think that you can go and take fundamental parameters of the architecture, like exactly what the pipeline size is and exactly what instruction latencies are, and plug them into something that's going to give you an optimal number. I think you're really going to have to do it empirically, just because there are a lot of complicating factors that go into these things. But nevertheless, those kinds of things are important, especially a trade-off like this, where you're trading off compute versus memory bandwidth and memory latency, because those things are very different on different machines. Oh, and here's an added benefit of this approach as well, which is that the answer is more accurate. The n log n approach is an approximation, right? This tree is like a monopole, it's the second order multipole approximation, and so the answer is not exact. Most of the error that you get in the approximation comes from particles that are close to you. So the more direct calculations you're doing, the more direct n-squared calculations that you're doing, the more accurate the answer is. And this is just a simple test that shows you, as you increase the number of particles in the leaf node, your average relative error in a calculation, in this case the calculation was just I have a ball of particles, goes down pretty quickly, actually almost to precision. Remember, we're dealing this in single precision. So 10 to the minus 6, 10 to the minus 7 is accurate to the last bit. So once you have over 10-ish particles per leaf node, it turns out, at least for very clustered configurations, that you're getting almost the exact answer. I think I said most of this already. The short-range force that we use is some sort of effective thing that came from a polynomial fit, subtracted from the thing we actually want to compute. When I say that we fit the force empirically, I should point out just one thing, which is that actually we fit it as a function of r squared. And with all these kinds of fitting formulas, CPUs are really good at computing polynomials. So you kind of want to compute polynomials whenever you can. But you do have to compute polynomials in the best variable. And there is some freedom there, right? So I mean, we could have made this polynomial in r instead of r squared, that kind of thing. So there is some freedom, and you do have to put some thought into it. I'm going to talk a little bit about how we do the various ways of doing the threading. Right, and so in terms of actually designing the kernel, I'm not going to talk too much about this, but I'm going to say the following. So one is that memory motion is important. In fact, memory motion is probably the most important thing to your kernel performance. And in addition, depending on how much data is being brought into your kernel, you may need to explicitly prefetch the data. The way you do this is different on different machines. How far ahead you have to prefetch is also different on different machines. But luckily, most compilers, like GCC and all things that are compatible with it, have a built-in prefetch intrinsic, so at least you don't have to worry about machine-specific assembly or anything like that. Most of the time, if you're just running through contiguous arrays and you're not running through too many of them at the same time, then the CPU will take care of the prefetching for you, and so the data will most likely be in cache by the time you want it. On the other hand, almost all machines, this is true in the Blue Gene, it's true in x86 machines, it's true on AMD machines and everything else. The automatic prefetching hardware has a fixed number of streams that it will prefetch. In other words, a fixed number of contiguous arrays that it will be able to look ahead and get the data into cache before you need it. If you're doing a 2D problem, then you might find it's not an issue. All your data, your performance is where you expect it to be, and all the data seems to be in cache when you want it. Then you move up to 3D. Now, all of a sudden, say, you went from bringing in 9 arrays to bringing in 27 or whatever. And now, all of a sudden, your performance really falls off much faster than you thought it should. Well, it could be that it's just the fact that, with the number of threads you're running or whatever else, your automated prefetching hardware just doesn't track 27 streams per thread. Like, it just doesn't like the hardware has a fixed number of tables or whatever that it uses to store those streams. You just ran out. And so what happened is now your kernel is really slow because most of the data that's coming in is not already in the level 1 cache. For what it's worth, on the Blue Gene, nothing ends up in the level 1 cache, which is a big problem. But and so you almost always need to do explicit prefetching unless you can hide your latency some other way. Another thing is, and people who care about having clean code will probably shoot me for saying this, but the compilers are actually not generally all that good at picking optimal loop unrolling factors. They'll normally get the answer about right, but if your code is spending almost all of its time in one or a few kernels, and they're loops that you can think about unrolling. You may want to think about playing with the unrolling factors. Most compilers will have some sort of pragma or something that you can use to force a particular unrolling factor. That means if you have a loop that does something simple, it may be beneficial to have a loop that has fewer iterations but has, that replicates the body of the loop a few times within each iteration. So you may need to play with that as well. The other thing is that modern computers are really designed to do one thing well, and that one thing is to compute fused multiply adds. In other words, A plus B times C. No, the other way around. Well, it depends on where you put the parentheses, but there's a multiplication and an add, right? So almost all modern machines, you get your maximum flop rate and your best computational efficiency by doing that and essentially only that. Well, what are those things good for? Well, essentially, they're good for computing polynomials, just because of the way numerics work, likely relatively low-order polynomials. Not order 1 or order 2 and not order 10 or order 9. So there's a pretty restricted range in which these things can be really optimally used. And in some sense, half the trick of this thing is getting your problem to be that. And the other thing that I want to say, well, maybe I'll say this first and then go back to slide, which is that modern machines also have estimates. This is true on the blue gene. It's also true on x86s. You get estimates for things like reciprocals and reciprocal square roots, which obviously doesn't matter to many problems, but does matter to, say, particle interactions where you have to compute distances. It also tends to matter in graphics and things, which is why the computers have these instructions in the first place. But the nice thing about these things, these estimates, so they give you an estimate. And the way these things work is that it gives you an estimate, and then you use some Newton iterations to refine the answer. If you, in your source code, have something equals square root of something, or something equals 1 over something, normally what happens is that the compiler will generate the instruction for the estimate, and then it will generate some instructions to do the Newton iteration. They're not terribly complicated instructions, but they're there. And the question is, well, how much accuracy do you really need? Maybe the term in your equation that has that square root in it is suppressed by a multiplicative factor of 10 to the minus 5. So that means, in single precision, you only actually needed the first 2 bits of the answer. I'm hand-waving here, but you get the idea. So if you only needed the first 2 bits of the answer to be right, well, then you didn't need the Newton iteration. You can get rid of a lot of the extra computation in your loop, which you actually don't need, by directly using the estimates. Generally, there's some sort of compiler intrinsic for that, and you don't need the Newton iteration. So that's something that you might want to consider. The other thing is that inside your loop, you don't want to have if statements if you don't need them. Simple if statements often get turned into instructions which we'll call selects. Different architectures have different names for these things, but essentially a select is the answer is either A or B, depending on some condition C. There generally is a single instruction for that, and hopefully the compiler can generate it for you. Really simple if statements, like min and max, that kind of thing, those normally don't actually end up as branches in your code, although I'll say something about this in the last slide, which may surprise you. But anything more complicated than that, you really do not want to do inside your loop. We have 2 ways of doing the parallelization for the fourth kernel. So one way is that within each leaf node, so each leaf node has a set of particles, and we have to interact those particles with some other set of particles that we've accumulated in an interaction list. We have 2 implementations of the threading for this. One is that in the very inner part of the kernel, we assign each particle, we sort of assign the particles in the leaf node to the various threads, and each of those threads handles the interaction of its particles with the interaction list. Nice thing about this is that all of those threads are sharing all of their data. They're sharing the interaction list, so they're not competing for bandwidth. In fact, that interaction list, once it's brought into cache, will be in the cache for all of those threads. And they can really all work together on the same data, sort of in lockstep. And the other thing is that, remember, we divide up the leaf nodes so that they all have about the same number of particles. As long as that number is is larger than the number of threads by some significant amount, each of those threads generally has the same amount of work to do. And I made a simple plot here that shows the thread scaling of this mechanism, so here, blue is perfect. This first mechanism I've just described is in green. And you can see it scales out to about 16 threads and then stops. And the reason for this has to do with the fact that our interaction lists only have a few thousand particles in them. And so once you divide that up over more threads than this, and you take into account how many loop iterations you're doing and the overhead for starting the parallel region in the first place, it turns out you don't gain anything over about 16 threads. So then we have a second mechanism. The second mechanism says that we queue up all of these interactions between the various, we queue up each leaf node interaction, including the part that builds the interaction list. And we divide all those up among the threads, and we execute those in parallel. The disadvantage of this is that all these threads are now competing for bandwidth because they're working on completely separate data. The advantage is that the interaction list building is parallelized, and there's a more work items to be divided among the threads. And as you can see, this is in red, scales much better. In fact, we can scale this all the way out to, say, 32 threads. So I said something about balanced concurrency. I'm just going to point out the following, is that when you use OpenMP to do your parallelization, when we use the mechanism where we queue up all these work items, we use this dynamic scheduling. And this actually is quite important because not all these work items have exactly the same amount of computation to do because they're doing this tree walk. When you normally put pragma OpenMP parallel above some loop, what the runtime system does is it takes a total number of iterations, it divides those as evenly as possible among all the threads, and just says, go. So the problem with this is if the work isn't balanced, then you're going to have a problem because some threads will be done much sooner than other threads. There's a really nice thing here. It says schedule dynamic, which says that each thread takes, say, one item off the queue, does something, and then goes back for another one. And it keeps everything much more balanced. When you're doing portable performance, one key about portable performance is, well, one, write as much of your code to be portable as possible. And this means writing it in some high-level language. So this is in C, but the example sort of applies to almost anything. So you're not writing in assembly or what have you. And you're relying on the compiler to do things that give you the performance you expect. So in this case, I'm looking at vectorization. And Jeff made a comment this morning which reminded me of this example. So I stuck it in at the last minute. Here I have a very simple loop. I have a function that takes 3 arrays. And what it does is it loops through some number of elements in the array. The number of elements is known. And it says, all right, if the value in C for any index is positive, then set A equal to B. Otherwise, set A equal to 0. This is a simplified version of the loop which is in the core of the HACC Force kernel on the CPUs, which essentially loops through some particles. And there's a particle cutoff, right? So it actually has 2 conditions in the HACC kernel. One is that the particles can't be exactly in the same position because then the distance is 0 and bad things happen. Or they could be too far apart, in which case the polynomial approximation isn't valid. But this is a simplified example of this. I was working on getting a function like this to auto-vectorize. I mean, so in the Force kernel, we've done this explicitly with vector intrinsics for various machines. But in principle, the compiler could do this, I thought, right? I mean, why not? And the reason why it won't, I thought, was fairly surprising. My first thought was, well, it's aliasing, right? The compiler doesn't know, that A and B and C point to distinct regions in memory. But no, I mean, that's what the restrict is for. And you can, there are ways of verifying that that's being interpreted correctly by the compiler. So it's not an aliasing problem. Shortrange, you don't have to put restrict because it gets those semantics by default. So I thought, well, okay, maybe it's alignment. Maybe because the compiler doesn't know that these arrays are aligned for the vector loads stores that it would need. No, you can tag the alignment too, and it still won't work. Anyone have any guesses to why this won't vectorize? Or I should say, you have to be more specific for me to really say you got the right answer. In order to vectorize this, and as I mentioned the selects before, right? So this is a very simple. This conditional won't actually end up as a conditional, right? That ends up as a single select statement. And in order to use that, the compiler would have to know that it's always safe to load things from this pointer, because it has to load them, say, 4 at a time or 8 at a time or something like that. So the reason why it won't ever auto-vectorize this loop is because the compiler can't prove it's always safe to dereference that pointer. Because what if all of these were false? This pointer could be null. It would never be dereferenced, and your code would execute just fine. So the compiler will not auto-vectorize this without some sort of explicit instruction, explicit non-standard directive, because it cannot know ahead of time that this statement will ever execute. And since it never knows that this will execute, it will not be able to vectorize a load based on that pointer. So this is my last point, is that it is sometimes helpful to think like a compiler. What I mean by that is that when you are compiling code and you expect the compiler to do the right thing for you, sometimes you have to realize that it has very limited information. And the things that it does have to be always right. Otherwise, it's a bug. And so this kind of example just gives you a feel for a reason why the compiler may not really do the thing that you think it should obviously be able to do.